This notes page is for solving radical equations and looking at their functions, but we're also just going to review rational exponents in case you come across those. So for any rational expression, m over n in lowest terms with n greater than 0, we define a to the m over n as the nth root, so that bottom denominator is the index, nth root of a to the m, and that m might be with the a or outside the radical. Okay, so we'll just practice a couple of these. It says rewrite each radical expression using exponents. So this is a two-step problem if you want to get rid of the fraction. So the square root, the understood index of 2, and the understood exponent of 1 are going to make the square root of 5 be written as 5 to the 1/2 power. And if you want to get rid of the negative, get rid of the fraction, you can use negative exponents. So if we move that 5 to the 1/2 to the top, that becomes 5 to the negative 1/2 over 1. So the fourth root of r, there's an understood exponent, so that's r to the 1/4. The cube root of x squared, that would be x to the 2 over 3 power. And I like these because they're, if you need to evaluate something in the calculator, that's actually a lot quicker to put in the calculator. So I like to convert my radicals to rational exponents. This one, the 5 is outside. Remember, that's the same thing as the cube root of b to the 5th, which is b to the 5/3 power. And we need to be able to go the other way. So you need to know what 4 to the 1/3 means. That just means the cube root of 4. And x to the 2/3 would be the cube root of x squared. This one is a two-step problem. Y to the negative 3/2 is the same as 1 over y to the positive 3/2. And then 1 over the square root of y cubed. So just kind of using rational exponents. Alright, last one is probably the biggest error that people make. It goes down to PEMDAS. This 5 is not attached to that a. This is a to the negative 3/2. You would have to figure out what that is and then multiply that by 5. So this 5 is not stuck to that a like glue, which is important because we want to get rid of the negative exponent. That's going to be 5 times 1 over a to the 3/2. Or 5 stays in the numerator like it was, but the a to the negative 3/2 goes to the denominator as a to the positive 3/2. So then that would be 5 over, index would be 2, square root of a cubed. So just a quick review of rational exponents. Alright, now let's review graphing, and we're going to use the translation method. So recall, I used to, back with quadratics, I called that the parent function. This is the parent function for all radical functions. Y equals the square root of x. And y equals the square root of x, let's recall what that looks like. When x is 0, the square root of 0 is 0. When x is 1, the square root of 1 is 1. When x is 4, because I can pick numbers that work to my liking, y is 2. When x is 9, y is 3. X can't be negative because you can't have a negative under the radical, so this is the shape of a radical function. We call that the vertex. It's got a vertex of 0, 0, and there's no vertical stretch. It's when you go right one, you go up one. And this is the parent function. Every radical is going to look like that unless you stretch it or shrink it or translate it, move it, or flip it. So we can review what's going on here. So the first thing we want to see is that the parent function is being shifted right 3. That minus 3 in there with the x shifts it right 3. It's the opposite of what you see. And up 4. So if this function is getting shifted right 3 and up 4, then that means that the new vertex is located right 3 and up 4 at the point 3, 4. I got a hole punch right where I need to be. There, 3, 4. Okay, now what does this 2 do? Well, if you recall, it's going to vertically stretch it by a factor of 2 because it's outside the function. So what's going to happen is you can take these ordered pairs from the parent function 0, 0, 1, 1, 4, 2, 9, 3 and just multiply the y coordinates by the factor of 2 and then just use that as your pretend origin. Let's put the new points down so we don't have to do too much thinking. That's going to give you 0, 0, 1, 2, 4, 4, 9, 6. Okay, so we can just take this point and pretend it's the origin. That would be the 0, 0. And then from it go over 1 up 2. Instead of over 1 up 1, go over 1 up 2. And then back to it. And then 4, 4, we're not going to plot 4, 4. We're just going to think, okay, I'm going to go over 4 up 4 instead of up 2. And then we're vertically stretching these by a factor of 2. Then we're going to go back to the origin and go over 9 up, not 3, but 6. And you get the same looking radical, but it's been stretched by a factor of 2. So we went over 1 up 2 instead of over 1 up 1. So we can graph these by translation. You can also graph those by plugging in points using your calculator to get you points, but that's one way to graph. Alright, let's try this one. This one has a vertex of negative 2, 3. Because this plus 2 is going to shift this radical left 2 and this plus 3 will shift it up 3. So if you go left 2 and up 3, you're at the point negative 2, 3. And then also this negative is going to flip the radical over the x-axis. So if I graph negative 2, 3, so here's negative 2, 3, and I can use these points and graph these points before they get multiplied by 2, but I'm going to flip it, so I'm going to go right 1 down 1 and then right 4 down 2 instead of up 2 and right 9 down 3, and you get this radical function that looks like this one, except it's been flipped and moved to the left 2 and up 3. Okay, so let's go ahead and start solving radical equations. The steps are right there. You want to isolate the radical just like you want to isolate absolute value. You want to raise each side of the equation, not each term, but each side of the equation to the same power. So what that means is, sometimes students make a mistake here. So if you had the square root of x equals x plus 4, and I'm not going to solve all this, and you wanted to square both sides. That's what we mean by square both sides. You can't do it this way. Square that and square that. That's really illegal because remember, a binomial squared is not, you don't distribute the exponents. So that's not what we're talking about. That's what step 2 means. You raise each side of the equation to the same power. And then just like log equations, you're going to have to check for extraneous solutions because radical functions, remember, whatever's over right here has to be greater than 0, greater than or equal to 0. So you have to check to make sure you don't have extraneous solutions. Alright, so let's get started. Step 1, you want to isolate the radical, which we have already. And then the index is 2, so the opposite of a square root is to square. So we're going to square both sides. That's going to give me 4 equals the square root of 4x squared. The square root and the square cancel and you get 4x. So now all I have to do is divide by 4 and I get x is 1. And then you don't have to necessarily check for accuracy, but you want to check to make sure that you don't get an extraneous solution. So if we put a 1 in there, 4 times 1 is 4, and the square root of 4 is 2. So that's the correct answer. When you find yourself squaring a negative, and it turns into a positive, that's a good indication you might have an extraneous solution. All right, we'll get there. All right, number 2, you have to isolate the radical. So we're going to divide both sides by 5 and get square root of 16x equals 64/5. Don't worry about that. The arithmetic we got a calculator for. So what's the algebra say do next? Right, we want to get rid of the square root, so we're going to square both sides. Okay, so that gives me 16x because the radical and the square cancel, and then we can use our calculator, parentheses 64 divided by 5 squared, and you get 4096 over 25. If you see that 64 squared, 5 squared. Now I need to divide by 16, which I don't like to divide by 16 if I see a fraction. I'm going to multiply by 1/16. That's another way to get x by itself. And then I can already have that in there, so I can just hit times 1/16 and get 256 over 25. All right, to check our work, we can just type in 5 times the square root of 16 times 256 over 25. And we get the answer 64. So we check that, that checks out. All right, you could try number 3. So if we square both sides, we get x plus 6 equals 9. Subtract 6, you get x is 3. Check your work. Square root of 3 plus 6 is supposed to equal 3. Square root of 9 does indeed equal 3. So that works. Okay, now number 4 is different. It's important. You gotta know how to do this one. So first of all, we have the radical isolated, so we don't have to worry about that. It's the only thing on the right side. So we're ready to move to step 2, and that is square both sides. And you have to square this whole side. So what does x minus 3 quantity squared equal? Does not equal x squared plus 9. This is another binomial squared, which I said you'd see just about every day. So I like to use my trick. If I multiply this out, x minus 3 times x minus 3, I'm going to do it a shortcut way, square double square, x squared. Multiply these two together, get negative 3x and double it, so that's negative 6x, and square that negative 3, that's positive 9. Square root of 3x plus 1 squared is 3x plus 1. Do you notice what we have? We have a quadratic, so you have to set it equal to 0. And this is where extraneous solutions come in. Okay, so x squared, subtract 3x from both sides and you get negative 9x. Subtract 1 from both sides and you get plus 8 equals 0. That factors, the factors of 8 that add up to be 9 are 8 and 1, and you want them to be minus 8 and minus 1, so they'll add up to be negative 9x. And then after you factor, you set each factor equal to 0 and you get x is 8 or x is 1. So now we have to check both answers, and I'm kind of thinking there might be an extraneous one. It's not always, but this quadratic, when that happens, sometimes it'll give you an extraneous solution. So this is the original problem, and I have to plug 8 in to see if it works. So on the left we'll have 5, and on the right we'll have square root of 25, and 5 square root of 25 is positive 5, so that one works. Alright, now I have to check the 1 and watch what will happen. 1 minus 3 equals the square root of 3 times 1 plus 1, so that's negative 2 equals the square root of 4. Now you might think that works because the negative 2 quantity squared is 4, but you did not bring this square root into the problem. That was the original square root. So when you're given the square root, it's the principal root, or it's only the positive one. So the square root of 4 Isn't 2 or negative 2? The square root of 4 is 2. And that's not right. So this one is an extraneous solution. So real quickly, I just wanted to show you what's going on with the graph. So I just put the right side in, square root of 3x plus 1, and I put the left side in, x minus 3, and graphed them. And you can see there is only one solution, 8, 5. This radical here, if it went over down here, then it would have an answer right here of 1. But there's a domain restriction on a radical, so it's only this branch, and that's why you only have one solution. Okay, so that's a great example. Check for extraneous solutions. Okay, back to these. Now we're at the stage where you look at this and you have to understand that you can't square this and this and this. That's extremely illegal. Step 1 is isolate the radical. So we have to add 2 to both sides and get the square root of 2x plus 3 is equal to 17. Now I can concentrate on getting the radical gone, so I'm going to square both sides. That gives you 2x plus 3 equals 17 squared, 289. Now we're going to subtract 3. That's 2x equals, oops, went too fast, 289. Subtract 3 and you get 2x equals 286. And divide by 2 and you get 143. If you check your work, I don't think there's going to be a problem because I didn't square a negative and I didn't have a quadratic to solve, but we can check it to be sure. And it's also a good way to check your arithmetic. So if I put 143 in for x plus 3, go to the right, minus 2. When I hit enter, it should equal 15, and it did. Alright, next one. What if you have 2 radicals? Now we're not going to get into really difficult ones with 2 radicals, but this one isn't hard because each of the radicals is isolated. So we just think, well, how do I get rid of the square roots? Well, I'm going to square both sides. So that's just going to give you 2x plus 5 and 12 minus 3x, because when you square a square root, they cancel each other out. So now we have to solve for x. So the first thing I like to do is go ahead and get my x's together. 5x plus 5 equals 12. Now I've seen a lot of students don't do that first, and it always messes with me, but I like to make it look like that. Subtract 5 and you get 5x equals 7. Divide by 5 and you get 7/5. Okay, so to check this out, we will put in the square root of 2 times 7/5 plus 5. And you have to kind of jot that down. The left side you get 2.79. Now we'll try the right side. Square root 12 minus 3 times 7/5. And you don't have to write it down. You can see on the calculator you get the same thing. So that is a solution. Now, number 7, we have our first rational exponent. So you've got 2 choices. You can rewrite that immediately as square root, because that 2 index, that exponent is belonging to 2x plus 1, and then go from there. Or you can just remember your algebra exponent rules. If you have a to the m to the p, you can multiply. Right? So if you have an exponent to an exponent, you can multiply. So if I want to get rid of a rational exponent, all I have to do is remember to raise it to the reciprocal of that power. So if I raise 1/2 to the second power, 1/2 times 2 is 1. That gets rid of it, which is what you would do over here. Okay, so that gives you 2x plus 1 equals 25, 2x equals 24, x is 12, and you can still check it using your calculator. Parentheses 2 times 12 plus 1 raised to the 1/2 power equals 5. Alright, now number 8, you have to isolate the absolute value again first. So we're going to subtract 2 and you get the cube root of x plus 1 equals, if we subtract 2, we get negative 3. Now, this is the first time we've had an odd index. And recall way back at the beginning of the semester, when you have an odd index, there's no domain restriction because you can have a cube root of negative 8, for example. There is a number that exists that when you multiply it by itself 3 times you get negative. Okay, so you can have a negative under an odd index radical. So this does not bother me that this cube root equals a negative number. Now this would bother me because remember, if you're given the square root, it's known as the principal root. It has to equal the positive root. So that is no solution. But this one, it can have a solution. Okay, so it's an odd index. So we're going to cube both sides like that. And that cube root of x plus 1 cubed is just x plus 1. And negative 3 cubed is negative 27. So you get x is negative 28. Alright, now if you want to check this work here, this is where rational exponents come in, or you can do this. If the index is other than 2, you can type the 3 in and then hit second and then this x to the square. You see that square right there? You can hit that button, and because you typed the 3 in first, it knows that your index was 3. If you don't type the 3 in first, then it's going to look like that. It's going to be like, it's going to say the answer. So you type the index in and then second and then that square root button. Okay, and we have to check it, so we have to put negative 28 plus 1 under the cube root plus 2, and when we hit enter it should equal negative 1. And it does. Okay. Alright, so you may want to try number 9 on your own. You're going to square both sides because that's a 1/2, so we can get rid of that 1/2 by squaring. So 3x minus 4 equals 36. Add 4 and you get 3x equals 40. Divide by 3 and you get 40/3. I didn't see anything unusual happen, but sometimes you can get in trouble by not checking. So I'm going to check it 3 times 40. Let's put parentheses around that. 40 over 3 minus 4. All of that to the 1/2 power. And when I hit enter, it should equal 6. It does. All that to say, I have missed this problem, number 10, so many times. Finally got the hang of it, know when it's coming. Got a 2/3 power, and that can be a little tricky. So, you know, if you want to be fancy, which I recommend, I mean, it's good, and you say, well, I know how to do this. If I want to get rid of the 2/3 power, I can just raise it to the 3/2 power. And you get 3x plus 4 is equal to 16 to the 3/2 power is 64. Then you get 3x equals 60. When you subtract 4, then you get x is 20. And so many times I've moved on and said, oh, that's the answer, 20, but that's not the only answer. So let me explain. When you don't change your rational exponent, sometimes it's kind of hard to see what's happening here. So let's rewrite it. So this would be the cube root of 3x plus 4 quantity squared equals 16. Okay, so if you solve it this way, this first thing you would do would be cube both sides, and the cube roots will cancel, but you still have 3x plus 4 quantity squared equals 16. 16 cubed is 4096. Okay. Now, how are you going to get rid of the square? That's right. You are taking the square root. And when you take the square root, so tricky, you have to remember to account for both plus or minus. See, all these other problems you had the radical given to you, so it's only the principal root, but this time you're solving and you're taking the square root, so you have to account for all possible answers, and so it's really a plus or minus 64. And I have missed this so many times, but not anymore. I have to go back and fix it. So what this means is you're solving 3x plus 4 equals 64, or 3x plus 4 equals negative 64. And we solved that one, we got x is 20. But we also have to solve this one, and you get 3x equals negative 68, and x is negative 68 over 3. So this one actually, I'm so sorry, this one actually has two answers. Very tricky. You miss it, and after I get so excited teaching students, you can use the reciprocal, you can use the reciprocal. Get so excited teaching that, notice that there's a 2 in this index. So you are taking the square root when you're doing that, and so it really should be plus or minus. So that's a cautionary tale to using a good technique, but it really is hiding the fact that you took the square root when you have a 2 in the denominator. If you write it out this way, then you are less likely to miss the fact that you're taking the square root, so it's plus or minus. So the answer isn't just 20, the answer is 20 and negative 68 over 3.